So, now we are in the 46th class in dairy and food process and products technology, right. We had finished with standardization, but to have a little more, so I am just showing it, I am not going through it because now we will go to milk homogenization. So, before that just showing that standardizing juice concentrates. So, this is one such way you can do the standardization, and that is simply by mass balance. So, by doing mass balance you can also do this, and using the Pearson square, which we have already said earlier. This is a more elaborative example of doing that Pearson square, how the Pearson square is being used. This is here being shown, and some examples we have dealt with, and these examples you can also work out and do that, right, using the Pearson square technique also. Now we come to homogenization. So, this homogenization is a very important step in milk, because as we have said earlier also that milk do contain fat in different sizes, right. So, ranging from say decimal micron to around 25-30 microns. So, these sizes are there, and fat do have common tendency to agglomerate. So, after agglomeration they become bigger sizes, and from that they do come out to the surface, right. This is by when we have said by Stokes law you can find out at what rate this fat will get separated given a diameter, right. So, to avoid that for a longer period, to keep the milk for a longer period at no separation of fat, the next step after pasteurization you have killed all the pathogenic organisms. So, after that you need to homogenize. So, homogenization is for the settlement, for the fixation of the fat content, right. So, that fat content will not reduce because of separation. To do that you need to do say homogenization. Now, homogenization is a physical process of breaking down the fat, right, milk fat globules into tiny droplets, small that will dictate at what, maybe 1 micron, maybe 2 micron, maybe 3 micron, that size you will decide, and to that all the bigger sizes will be brought down. Of course, smaller sizes you cannot elevate, but the bigger ones will be brought down to the smaller ones to discourage cream separation. Tiny droplets of fat do not rise in a milk column, since reducing their sizes also increases their density in the milk, because more the size, bigger the size was there, less was the number. Now, less is the size, bigger will be their number. So, more fat dense will be there in the particular, or in a density in a particular one, or uniformly it will be. A milk homogenizer is working at between 100 to 170 bars that splits all the fat globules into very tiny droplets that increases the level of integration of the fat in the milk. As a result, the milk fat remains ununiform, or rather milk fat remains uniformly distributed in the milk, right. Now, there is a heating section, because milk homogenization subsequently seen that homogenization is also a function of temperature. The higher the temperature, better is the homogenization, right. But there is also an optimum. It is not that it will go on increasing like this steadily, right. It will not go on increasing like this steadily. That is also there, that if it will go like this, it will be like this. So, there will be some optimum or maximum where the temperature is good. So, that is why it is that about 60 to 72 degree centigrade is effective to kill the Clostridium botulinum spores. The steam exchanges heat with the milk across the plate heat exchanger in a counter current motion. At the same time, at the end of this section, there is a temperature sensor which controls the flow diversion valve. Any milk that does not attain the required temperature is diverted back to the heating section until it attains the required temperatures. Right. Once you got the temperature, then holding section. There is after heating, milk flows into the holding tubes whose lengths have been calibrated with the milk flow rate to ensure that the milk takes at least 16 seconds in the tubes. This holding time is 16 seconds in the tubes. All the milk must remain in the required pasteurization temperatures at the end of the tubes. So, in case of a breach, a sensor will trigger the flow diversion valve to take back the milk to the heating section to bring the milk to the required temperature. Once the milk has attained the required temperature, at the end of the holding tubes, milk flows back to the regeneration section to heat the incoming chilled milk, while in itself being cooled down to about 30 degrees centigrade. Now, after that, that is, this is again back to pasteurization. After that, it goes to chilling or cooling, which again is being done by a plate heat exchanger, so that it is brought down to, after pasteurization, brought down to 4 degrees centigrade, and the chilled milk is then pumped to the packaging machines for aseptic packaging. Okay. But before that, this is homogenized, which we have said that this is done, right. This is microwave heating, this will come afterwards. Ohmic heating will come afterwards. So, high pressure processing will pass electric field by non-conventional thermal, non-thermal, right. So, while homogenization we do that, homogenization what it does, pasteurized milk around 100 to 125 atmosphere is allowed to pass through a homogenizing valve, right. This homogenizing valve, it does the homogenization, right, as given in the next figure. We will show the figure. Figure is like this. Let us go back to that figure, which will be easier to understand. So, this is that homogenization is being done here. So, milk is flowing like this, right. So, these are the fat, bigger fat globules, they are moving, right, through this slit. This is the slit gap, right, this is the slit gap. So, through this slit it is going. I hope if you had gone through our earlier class, that was on your the naming of the class was not on milk, that was a general class on the fluid flow, right. The fluid flow, if you had gone through there, you might have seen that the velocity profile and all others we have done when it is flowing through a slit like this, right, that we have done. So, there we have not taken like this the fat globules, we have taken a general fluid, but and there we have shown the velocity profile, how the velocity profile is coming like this, right. Okay. But when these fat globules are going through this slit, whose size is according to your desirable size, what you want 2 micron, then this size will be 2 micron. If you want 3 micron, then this size will be 3 micron. So, according to your requirement, this is right. And okay, this is the seat, this is the forcer which you are adjusting what the distance will be or how the pressure will be. So, this is going that homogenized fat globules which are of smaller size like this, right. These are the smaller sizes, homogenized product is going, right. So, this is the homogenization valve. So, if we go back to that, then we say that the valve seat and the valve are made cylindrical, made of cylindrical structure. Upward force exerted by the homogenized milk on valve seat must overcome the downward force exerted by spring on it. Milk flows out radially through the passage between the valve and the seat. During the process, what happens? During this process, we have already shown the valve. So, during this process, the fat globules are sheared, right. This is the fat globule, this is the fat globule. So, a force is acting like this and like this. So, by that there is a shear action on the fat globule, and these fat globules then, if you look at the other figure, it will be like this, right. So, this is the fat globule. So, there is a shear action that is happening like this, and because of that the fat globule is getting, say it is the enlarged view like this, they are getting segmented, right, and ultimately this is becoming the intermediate, become wavy and constrict, right. So, this is the action of the force, this becomes wavy and constrict, and this disintegrate into the individual droplets. From this bigger droplet to the smaller ones, they are getting by the shear action. So, this is splitting of globules by homogenization, this mechanism follows, right. So, now we go back to that. So, that is what is happening in the homogenization valve, that if the rate of shear is large, globules are elongated, ripples are formed on their surface and finally break into smaller sizes, as we have shown in the next figure, right. As milk flows out radially along the face, say B, that is not we have not shown here, right. So, along the face of the valve, the velocity reduces due to the increase in the cross sectional area, right. Velocity is highest at a point, say A, depending on the milk velocity at that point. This will result in cavitation, formation of cavitation, and pressure of milk will increase as it moves radially outward from the center of the valve, that is from the point A to the point B. So, that if we can see this, so radially here, okay, radially, so that means it is going like this, right. So, if this is the point A and if this is the point B, according to that what we are referring to, right. So, that is how it is. So, from point A to point B. Homogenization of milk is due to the effect of shear on the fat globules and not on the cavitation. Though there will be cavitation, but the fat globules are disintegrated into smaller ones by the shear action, right. This shear action takes place, and that is what. Now, in that cavitation, one thing which we may not be able to explain in more in detail, that you know that if there is pressure in a bubble and then it gets exploded, right, that is called explosion. The inside pressure is more than the outside pressure. But if it is the other way, if the outside pressure is more than the inside, then that is called, earlier it was explosion, now this one will be called implosion, right. In cavitation, that implosion takes place, and by which the fat globules also get disintegrated, right. This also you keep in mind. Then this we have already said. So, after the fat globules are broken down into smaller size and came out of homogenizing valve, they are found to remain sticking to each other from a cluster and forming a cluster. In order to break the cluster and disperse fat globules, milk is passed through another homogenizing valve, that is the second homogenizing valve, and this second homogenizing valve takes place second homogenization, and the pressure is around 1/5 to 1/6 of the first, right. So, let me see whether we have this second valve. No, here we did not, because of the time constraint, perhaps we have not taken that. However, this second homogenization valve, so that is like this one from here, which goes to another valve, this one, it goes to another valve, right. Along with this, say this is one valve, and this is acting around, say, 2500 psig, right, 2500 psig. If this is acting at that, another valve similar to this, that works around 1/5 of this, that is 500 psig, right. So, that is called, this is called first stage, this is called second stage homogenization, that is two stage homogenization, right. So, if we take that, then we can say that in the second homogenization, it is taking place at around 1/5 of the first, that is if the original was 2500, now it is 500 psig. Why it is required? Because when the first stage homogenization, from the bigger one to the smaller ones it happened, these smaller ones start to agglomerate again and again become bigger one, right. So, that in future, in further, this should not happen, that second stage is there, and which works at much lower pressure than the former one, around 1/5 of the former one. Say if the former one is 2500, now it is 2500 only psig, that is why I am saying, because in bar it will be much less in number. So, so it is, and you can convert in atmosphere, in Pascal, so those are convertible, but since the number is unique 2500 psig and this is 500 psig, that is why I am giving the reference with respect to psig, so that the numbers you can remember 2500 and 500. So, these are the two stages, and this in the second stage this agglomeration gets further ruptured and then permanently it is formed into the smallest size as you have decided, 2 micron, 3 micron, whatever, right. Now, what are the effects of homogenization? Effects of homogenizations are like that, the homogenization increases its whiteness, larger number of fat globules are produced, that is why light is scattered. Then viscosity increases, and this is increases the shear force created by the presence of large numbers of fat globules. Then temperature is also increases because of the friction on the homogenization valve, as milk flows through it at high velocity, temperature is also increases. And fourth one is the gel strength. Gel strength during milk curdling through microbial formation, acids joins the milk protein present on the globules membrane. So, gel strength increases. Fresh milk contains lipase enzymes, resides outside the fat globule membrane and hydrolyzes that and transforms into free fatty acids when comes in contact with the fat. This is not desirable and undesirable for human consumption beyond a certain level. So, lipase enzyme has to be inactivated, and this is done during both pasteurization and homogenization, both are at high temperature, right. Now, during homogenization, there is a likelihood of lipase enzymes to be active in contact with milk fat increases. To inactivate, this is heated up to 65 degrees centigrade before homogenization, or 80 degrees centigrade a coagulation of whey protein. If it is beyond 80, this is done at 65. If it is beyond 80 degrees centigrade, then coagulation of whey protein occurs, because we said whey protein is a soluble protein, but it is soluble till the temperature is low. Solubility goes down if the temperature goes beyond 80 degrees centigrade. So, that is why you cannot heat beyond 80 degrees centigrade, otherwise that this soluble whey protein will come out or separate out from the milk, right. If we look at, this is a true picture of the valve where it is going through. The fat globules are like that, right. It is getting shattered and then becoming smaller. You see the time scale given is around 1 to 10,000 second, right. 1 upon 10,000 seconds, that time it is happening, and velocity or valve clearance is around 300 micron. And this is the schematic presentation of the homogenization process. Velocity of 0.3 to 3.5 meter per second is the fluid, that is milk velocity that is occurring. Fat globule size is between 1 to 10 microns, say. Velocity of around 100 to 200 meter per second is at the inlet, and because outside it was low. So, the moment it is going to the smaller diameter unit or smaller size, velocity is increasing drastically. Valve is around 200 kg per centimeter square, that is the pressure is being applied, and there global deformation take place like this. This was the one from where this is gradually deforming and then coming to that. So, homogenized fat globules between 0.1 to 3 micron as you are deciding that is being produced, right. So, this is the flow diagram or the pictorial diagram of the fat globules, and the valves are like that. There are different types of homogenization valves, different ways, different types, right. And you see, depending on this is the flow diagram. So, they are going through this, one is such, another is that this is going a zigzag path like this, right. Then another one where the slit is here, so going like this. The another one is tapered like this, going like this, this is tapered, right. And the fifth one could be there is a baffle in between, and that is going through that. So, depending on that, different size, different type, different geometry, they will be different configuration, there will be different type of pressure generation, and different fragmentation also will happen, right. So, this is a generalized homogenizer. That homogenizer looks like that, the pictorial view. Homogenizer looks like that. Hopefully, in any dairy industry or institute, this type of homogenizer is there, and that will dictate at what pressure. There are two stages. One pressure is generally 2500 psig, and another pressure is 500 psig. Right. This is the pictorial view of the valve. Right. And milk travels through the homogenizer machine where the fat, that is cream, is broken in uniformly. Right. So, this which I was looking for, that the two stage, this is the typical two stage valve or picture as we had given figure 2. This is like that. Okay. This is the first stage, this is the second stage. The milk is flowing through the first stage, again getting agglomerated, and through the second stage it is coming to the smallest size as you have given, right. This is the two stage homogenizer valve, right. The theory is like this. Let us go quickly. Many theories of the homogenization of high pressure homogenization have been presented over the years. For an oil in water dispersion like milk, where most of the droplets are less than 1 micron in diameter, two theories have survived. Together, they give a good explanation of the influence of different parameters on the homogenizing effect. The theory of globule disruption by turbulent eddies, that is microwhirls, is based on the fact that a lot of small eddies are created in a liquid traveling at a high velocity. Higher velocity gives a smaller eddies. If any eddy hits an oil droplet of its own size, the droplet will break up. This theory predicts how the homogenizing effect varies with the homogenizing pressure. This relation has been shown in many investigations. The other one is like this, that the cavitation theory says that, on the other hand, this cavitation theory claims that the shock waves created when the steam bubbles implode disrupt the fat droplets. According to this theory, homogenization takes place when the liquid is leaving the gap. So, the back pressure which is important to control the cavitation is important to homogenization. This has also been shown in practice. However, it is possible to homogenize without cavitation, but it is less efficient, right. So, we have ended up to this class. Thank you.